So we've taken a look at pop particles for the mechanical bugs' flight paths and for the particulate trails coming from those mechanical bugs. And pop particles work really well for simulations like this. But now we're going to take a look at grain simulations. And we're going to use grains for a disintegration of one of these creatures. And you can use pop particles to do grain simulations, but generally the Vellum solver is going to be a bit better for these types of sims. It's a newer implementation of grain simulation and has added benefits like being able to interact with other types of Vellum objects. And we're going to focus on Vellum for our disintegration of the character here. And if we dive inside the disintegration and just create a DOPNet, I'll show you just briefly that we do have a pop grains DOP node available to us here, and this allows some interesting self-collision type behavior from standard particles, and feel free to explore this if you'd like, but generally speaking, Vellum grains are typically preferred for simulations like this. And let's exit out of this DOPNet we just made, and we're going to be disintegrating one of the squid-like creatures in the scene here. So let's object merge that in, and we'll point that object merge to obj slash creature slash out creature. And grains tend to be fairly sensitive to the scale because they're self-colliding. So p-scale is very important to grains, and these will be initialized with a correct p-scale based on the grain size that we create these particles with. So to make our lives a little bit easier, I'm going to apply the scale that we're applying when we attach these creatures to their flight paths. So I'm going to pin my viewport to the disintegration network here, and then I'm just going to check the scale that we're using on the creature flying basic section here. And the creature scale that we're using there is 0.7. So I'm going to copy that transform, go back to our disintegration setup, and we'll paste that transform in here. And for the flight paths animation, we had rotated this 180 degrees, but we don't need to do that for our grain simulation. So let's remove that 180 degree y-axis rotation. So we're just getting the scale here. And we could fix the scaling later, but I'm just going to make our lives a little bit easier by creating the grains at the correct scale now, rather than trying to fix the scale of those grains once we apply the creature animation to the grain particles, as you'll see in a little bit. So now that we have this creature scaled to the correct size for our scene, we can convert this into grains by using the Vellum configure grains SOP here. So drop that in there, connect that to the creature scale. And our creature is still pretty big after being scaled down. It's 72 units long, so this is going to create some very dense grains. So for our initial tests, let's turn the grain size down a bit. Actually, let's turn the grain size up to decrease the resolution, because a larger grain size means fewer grain particles. So let's try a grain size of 0.4, and we're going to create points from volume to fill the entire volume of this creature with grain particles. And then when you display the Vellum constraints grain, you can see that's filled this entire volume of the creature here. And this is looking fairly low resolution, so let's reduce the grain size a bit to increase the resolution there. So a grain size of 0.3 is creating about 150,000 particles, which seems pretty reasonable for our initial tests. And the first output of the Vellum constraints grain will be the grain geometry particles themselves, which is what we see in our viewport here. And the second output will be the constraints that define this grain behavior. So if I drop in another null and attach that to the second output of the Vellum constraints grain, you can see that this gives us just a whole bunch of points that represent the grain constraints. And we don't really need to worry about these grain constraints themselves or mess with them, but we will need to include those in the inputs to the vellum solver in order for our grains to work correctly. So we'll attach the grains themselves to the first input of our DOPNet here, and the grain constraints into the second. And then inside the DOPNet here, we can create a vellum solver and attach that to our output. And we'll also create a vellum object for the solver to process, attach that to the first input of the vellum solver here. And typically, I use a vellum source instead of just the initial geometry and initial constraints available on the vellum object here. It might work just fine if you just leave it using the initial geometry and constraints as set up in this object, but my workflow is to typically use this vellum source and connect that to the third input here. And the default emission type for the vellum source is only once, so this will only be added at the beginning of the simulation. And we can grab these expressions from the vellum object to create the initial data that the vellum source is pulling in. So this vellum object here has a default parameter that will grab the input into the first input of the DOPNet as its initial geometry, and it grabs the second input to the DOPNet as the initial constraints. So we can just copy these or cut those out of there, and we'll put those in the vellum source instead. Do the same thing with the constraints. I'll cut that, put that in the vellum source as well. And then finally, let's add some gravity. And to see our grains in action, let's just see them piling up on the ground to begin with. So I'm going to add a merge and drop that under the gravity. And let's create a ground plane, attach that to the merge here, and we'll switch the input order on that merge since the default effector relationship is that the left affects right, so we want the ground plane to affect the vellum grains. So it's important for the ground plane to be on the left of the grains in terms of the merge input order. And for the ground plane height, let's check what the minimum height is on our input to the DOPNet. So middle mousing on vellum constraints grain shows the minimum Y value as -6.6. So let's set our initial ground plane height to be a little bit lower than that. I'll set it to be -8 for our initial tests. And let's exit out of our DOPNet. And right now this ground plane is displaying pretty small. So if we go back inside the DOPNet, we can change the grid size here. And the ground plane will collide much further out than this visual grid here. This is just for visualization purposes. So let's just extend this out maybe 200 units. That'll be more than enough for our needs here. And exit out of the DOPNet, and let's run this simulation to see what it looks like. So after flip booking this initial sim, you can see that we do have a lot of self collisions happening, and there's some nice pileup happening of all of these particles, but it's very bouncy. It doesn't really feel much like a nicely clumping type of material that we're really looking for out of this grain sim. So let's take this initial setup and finesse this a bit for some nicer behavior. So a few things we can do are to, well, first of all, let's reduce the bounce on the ground plane, because bouncy effect sims often look fairly unrealistic or amateur. So I always try to turn down bounce quite a bit from their defaults. On the ground plane, I'll set the bounce to 0.005. And generally with grain simulations like this, we'll probably need to use more substeps. So 5 is a good starting point for this, and you can feel free to increase or decrease that as you feel like you need more solving accuracy. But 5 is generally a good starting point. And then if we go to the Advanced tab, there are some grain collisions controls that are really the biggest part of defining some interesting grain behavior. So the attraction between grains is one of the coolest properties that really makes grain simulations look nice. And right now we have attraction between the grains turned entirely off. So it's almost like all these grains are just behaving like rigid marbles and just bouncing away from each other. But when we want something to disintegrate or feel more like, kind of a clumping sand or something like that, we'll need to use some attraction weight to simulate that. So let's turn the attraction weight all the way up to 1, and we can crank up the attraction amount as well to a higher value. Let's try 100, and then let's run a new flipbook and see what this looks like. And reviewing this updated sim, you can see the grains are now behaving essentially like a soft body object, and all the grains are sticking together quite strongly with those increased substeps and the cranked up attraction weight. And those grains are still allowed to pull apart from each other when the forces applied to the grains will overcome the attraction force between them. You can see the tentacles are snapping off from the body here, and this allows us to create some pretty interesting effects. And really, we don't want this whole creature behaving as one glob of strongly stuck together grains like this. We want to have some chunks that are kind of sticking together and some grains that are allowed to break free, and we want some variation in the size of our chunks as well. And to create some more interesting attraction clumps throughout these grain particles, we can apply some noise to the attraction weight attribute. And as a little hint to the attribute that you will use to override the attraction weight behavior, if you dive inside the DOPNet, look at the Vellum solver, and on the grain collisions section, under the attraction weight, if you hover over that, you can see the parameter is called attraction weight, and we can use that same attribute name to override the amount of attraction for each of these grains. So let's jump out of our DOPNet here and drop in an attribute adjust float on our grains here. I'll drop it after the first output of our Vellum constraints grains. And for the attribute name, I'll set this to attraction weight. And it really helps if we can visualize the noise that we are applying to this attraction weight here. And you can use visualizers in the viewport, but I still have the habit of using some color sops to visualize attribute values. So I'm going to set on this color sop a ramp from attribute, and I'll set the attribute to attraction weight and display that. And right now everything is showing up as black. We can double check to make sure we're seeing our particles correctly with our point display here. So let's check on our attribute adjust float to see if things are being set correctly. So on our attribute adjust float, right now we're adding a constant value of 0 to this attribute, which is just going to give us a value of 0 on everything. So instead of adjusting with a constant, let's adjust with noise. Now you can see we're getting minimum and maximum values of 0 to 1, and we're getting this noise pattern appearing across our grains here. And we can adjust the element size to control the size of these clumping features here. So I'm going to create a couple different scales of attraction weights here. We're going to do a larger scale attraction weight for some larger clumps, and then we'll fine-tune this a little bit with some smaller scale variants as well. So for this initial attraction weight adjustment, I'm going to set the element size a bit higher to 10, and this will give us some larger clumping between those grains. And if you want to take this same general element size but limit the size of the clumps that you're creating, we can change the value distribution here to uniform with remapping. And instead of going all the way from 0 to 1, we can change this remapping range here, and we can take this lower point position and bring this up a bit, and essentially use this remapping to define much tighter clumps rather than a broader noise that kind of encompasses the whole object. So increasing the bottom portion of this ramp quite a bit allows us to define some pretty strong attraction clumps that create some really interesting larger scale shapes here. And then we can use a smaller scale noise to create some smaller shapes on top of these large ones that we're defining first. So I'm just going to call this first noise adjustment large clumps, and we're going to make a copy of this to create some smaller clumps as well. So let's copy that and then place that underneath the large clumps. I'll call this one small clumps. And let's reduce the element size quite a bit. I'll turn that down to something like 2. And right now these smaller clumps are just as strong as the large ones. And I want the smaller clumps to be a bit weaker. So instead of going from 0 to 1 on the smaller clumps that we're adding in here, let's go up to our min and max values. And for the min value, I'm going to raise that up from 0 so we always have at least a tiny bit of attraction between the grains. And for the max value, I'm going to turn that down to 0.2 so we have some attraction, but it's not very strong. And then on this remap ramp, you can change this as well. So maybe I'll turn that up a little bit to have a little bit more precise definition on these smaller attraction clumps here. So you can see now we have these brighter sections with strongly held together attraction weights and these kind of mid-scale grays that are going to be still some, nicely attracting grain clumps, but they won't be quite as strong as these large-scale ones here. So now let's rewind our sim and do a fresh flipbook to see what it looks like now that we're overriding the attraction weights on our grains here. So now checking our new simulation for the grains with this attraction weight noise here, we're getting some cool effects, but it's actually exploding after a handful of frames here. And this is one of those things you may find yourself wrestling with a bit when you're doing simulations like this. And one of the things that we can try when we're getting explosions like this, particularly where things look like they're working properly and then just completely explode like this, we can try just increasing substeps to see if that addresses it. So I'm going to go back inside my DOPNet here and back to the Common tab and increase the substeps up to 10. And let's see if this increases the stability of our simulation. So now with the Vellum substeps increased to 10, you can see the issue with the exploding simulation is now gone, and we're getting some really nice clumping effects driven by that attraction weight attribute that we've set up in SOPs. And I think this is a good point to end this video, and next we'll take a look at some further customization of our grain behavior and setting up some manual constraints in addition to our noise-driven attraction weight.